I am Makini Valentine. I attend the New York City College of Technology in Brooklyn, New York. I've been doing this research project for over a year now. I'm a part of the civil engineering department. I work with a famous professor in that department, Professor Naruzi. He focuses on remote sensing, and I was really interested in this area of science and technology because I'm into environmental also, and I like the ideas that he have presented. The name of my project is the validation of downscale satellite land surface temperature in urban areas using an unmanned aerial vehicle and in situ application. Um, we are sponsored by NSF and NORCREST in this project. So we have been inspired to do this project mainly to analyze the different land surface temperatures in urban areas. As we all know, urban areas are densely populated with materials, impermeable materials such as asphalt, concrete, black roofs, and less vegetation. And that creates that heat wave and then creating that urban heat island effect that many of us are concerned about because it has a big impact on humans. A lot of people get sick around this time, especially in the summer with that large heat waves that pass over. And we want to analyze those different surfaces that causes this great heat influx. The objective of this project is to examine and to compare the land surface temperature obtained from the in situ data, meaning the land-based applications that we use, and satellite-based observations in order to understand the diurnal variation and heat transfer at each temperature surface. So here are the different land covers in New York. I identify how much of buildings are in the red color, and it just shows the density of these areas, how compact they are in New York City. And you can see there's less vegetation also, which is what we are analyzing, mainly the different surfaces in these city areas. To further understand this concept, so we have surfaces and the heat now is being absorbed from the sun, and that heat usually should be radiated or emitted back out into the atmosphere. But as we can see, one of the reasons why and what we are studying is that these heat fluxes are being absorbed more in these surfaces. And as we further study, we're going to see which surfaces are there that have been absorbing much more of this heat. And with respect to the satellite observations that we have been collecting, so we want to validate how these surfaces are being analyzed and downscale it in a way where we can have much more accurate results. So GOES satellite and Landsat satellite are the two satellites that we use to compare. The GOES satellite, as you can see here, there's a larger pixel size. And for the Landsat, there's a smaller pixel size. So therefore, with the Landsat, you can get much more accurate temperature results compared to the GOES-R. The problem that we have is GOES-R has a better temporal resolution, meaning that it takes pictures, it collects data actually every 5 minutes compared to Landsat, which is every 14 days. So with the Landsat, the spatial resolution is much better with a 30 meters pixel size, and the GOES-R is like 2 kilometers pixel size. So we use more the GOES-R because we take images on the ground scale using, I will further show you. We also use the Flux tower. This measures the energy balance, humidity, air temperature, and air quality, and also precipitation. This is one of the ground-based applications that we use. The thermal camera is a FLIR T650 thermal camera. It measures the surface temperature of different materials. So here are the different materials that we use: concrete, asphalt, and grass. These are the actual images of the surfaces. And these are thermal images that we collect using the thermal camera. We get the average temperature of these surfaces and then we graph them to demonstrate our results. This is the drone that we use, that aerial equipment that I spoke about earlier. This has a better spatial resolution also. We are able to downscale the data that we collect even further from the satellite to using actual equipment that we can measure on a smaller scale, meaning as we get closer to the surface, we get the actual temperature of the surface rather than with the satellite. It's more further out. So therefore we will get like a larger area of the city area more so. This is one of the photos that we collected at a park in Brooklyn with using the drone. We were able to subset this image to get the actual surface temperatures. Asphalt, as you can see, that area of the park, we got the asphalt. The grass, we got that area of the park with the grass. We got trees and rooftops. This is a thermal image that we got with the drone also. And these are some of the results that I collected in 2018. As I said, I was at this project almost a year and something now. And this was over the summertime. So the summertime is mainly when we focus our results, our data collection, and to accumulate some results. We have different surfaces here. We have grass, rooftop, trees, asphalt, that goes our satellite, and air temperature from a flux tower. So as you can see, the asphalt has a higher temperature compared to most of the other surfaces. The gozar is in the blue to the left with the drone. That has a more diurnal effect. Diurnal meaning it's every day, and the linear effect, sorry, that the gozar has doesn't really show much change. So by us using the drone and the cameras, we're able to get actual surface temperatures changing throughout the day, meaning that we get it from every hour, from morning to evening. So we do it 10 a.m., 11, 12 p.m., 1 p.m. Every hour we go outside by close to our school and collect this data. So with the camera, we're able to also get similar results every hour. Again, this was also summertime. And we can see that the asphalt is also, again, very high in these urban areas and most of the time in concrete and in the grass.
2 minutes left.
Okay, thank you. Winter results 2019, we can see that these results on the left, um, the different asphalt, concrete, grass, and air temperature are the surfaces that we use and try to compare in a way to see these results and these temperature change throughout the day. The other image to the bottom has a much more variation. This one was done with the drone. We got more surfaces, asphalt, concrete, soil, rooftops, and using the GOES, our satellite, and their temperature. As you can see, rooftops have a higher temperature in the summertime. Sorry, it's not summer, winter. Also, because of the black roofs, and that is able to absorb much more energy than probably a white roof. So summertime again. This was last year, summer. We were able to go to another park and was able to use the drone because it's very hard to get the drone up and running in the city areas. So we try to more locate park areas. This standard deviation process that I analyze, it shows how the change of variation in the different surfaces, the temperature in the different surfaces. And the asphalt seemed to have a much more steady variation compared to like the asphalt changing. A lot of problems that we have is the clouds. When there's a cloudy day or something, the temperature might change compared to a full sunny day. Those are some of the problems that we have with collecting this data also. Some of the conclusion, what we concluded so far, so we can see that this information in developing a heat stress product for cities when high resolution data from different services are used to predict their corresponding air temperature. The results of the study will shed some light in understanding heat storage in urban regions by providing a valuable boundary condition information at the surface for urban canopy models. Future work, the Flux tower that we have, it broke down somehow, so we've been trying to fix that, which is near our school in Brooklyn. It's like right behind the car park in by our school, and we want to be able to place that on a rooftop with different surfaces. Because by placing it on different surfaces, we're able to get the different temperatures around that surface. And we also want to get more diurnal variation, meaning throughout the day as the temperature changes. Early in the morning and more night observations. That's always been a challenge because a lot of people have classes, and the manpower that we have is not a lot right now. So that's the end of my project. Um, I like to thank NSF and everyone else included and my professors. And that's it. Thank you very much.